I wanted to explore possibilities for practical things you could do while being directly connected to solar panels without the traditional solar setup, specifically no charge controller, no batteries, no inverter. I settled on trying to make something that, in a perfect world, I'd want panels to directly power instead of having to go through complicated and expensive intermediaries. So I figured I'd make a complicated and expensive thing that I could add supplementary cooling to the house's AC. As you probably already guessed by the title, the easiest way I figured I could do this was via Peltier plates. To get a couple things out of the way, I know Peltier plates are inefficient. By a long margin, the compressor-based cooling system is the much more efficient way to go. There are some limitations of that kind of system, which I'll talk about later, but that ultimately led me to choosing Peltier plates. The reason I'm making this video is because I wasn't able to find many things about this very specific situation I've chosen to try and tackle, so in the hopes that if someone is looking for information in the future, this video might help. For the order of events, let's better define the goals and restrictions of this setup, go over the limitations of this kind of thing, followed by the finished product, and then I can get into the nitty-gritty details of the build process and information I found that might be common knowledge to those with electrical experience, but something I struggled with initially. As stated before, the primary goal was to power a load while being directly connected to solar panels, which means no charge controller, no batteries, and no inverter that a traditional solar setup has. The other goals and restrictions of the project that I defined as I went along was that this needed little to no maintenance, but also that when the sun came up, it's on and it turns off when the sun don't shine without the need for manual intervention. Lastly, since it seems that 100-watt solar panels are the most common, popular, and cheapest thing that people can purchase on Amazon or eBay, they typically run about 50 cents a watt. I wanted this to be usable with a 100-watt solar panel, and note that I said 100-watt solar panel and not less than 100 watts, and that's important for later. I feel like it's really important that I get this out here early, is that Peltier plates are inefficient. I just want to make sure that people know that I know that. For a lot of the things that I wanted to do, there wasn't a lot of information that was easily available, especially on the topic of directly connecting loads to solar panels. There's not a lot of practical information about this that relate directly to what I was trying to do. There was a YouTuber I found that had touched on the topic of directly connected Peltier plates, direct resistive loads for heating, and other things that were incredibly helpful, and I'll link his channel in the description. He unfortunately only really did larger scale uses with more or less full power Peltier plates, which again was helpful, but it wasn't really what I was looking for. A lot of things you see about Peltier plates are showing them at full power using hundreds to even 1,000-watt for really large scale, but it's only really touched on in forum postings that they work at much lower voltages with a higher efficiency coefficient, which isn't saying much, but I'll take what I can get because it's very, very important for this setup, and them using less watts overall was also super useful. It's really important to know that this is a very niche thing that I'm doing, and it definitely won't replace a standard AC unit to cool a whole room. This is for very small scale areas, or in my case, supplemental to whatever you're already doing. Like a small room is way too big for this, so just take that into consideration. Lastly, as to why I didn't go with a compressor-based system, based on everything I've seen, compressors don't really operate in wattages less than 100, or those that do are really, really expensive specialty items. Typical refrigerator compressors were about the lowest power I could find at 120 to 150 watts. They also tend to have surge power draw when kicking on, and I'm not really sure if that panel could handle that without a few dozen supercapacitors, and at that point you're already halfway to a battery. Their power consumption is less of an issue than the fact that in my very limited experience they're really picky about their power supply, or they're a hell of a lot pickier than Peltier's. There's the initial problem with the solar providing too high of a DC voltage, and this could be handled by a particularly robust buck converter, but the more troublesome issue is how compressors handle intermittent power outages. Troubleshooting a fridge in the past has taught me that unplugging and plugging in a compressor-based system in quick succession overloads the system and trips the safeties built into the compressors, probably because of, or possibly because of, where the compressor is in the cycle. The internal resistances of the compressor are magic as far as I know. Due to the intermittent nature of solar, because of clouds or a bird casting a shadow or whatever causing a dip in power, I felt like this was a huge hurdle that I didn't have the expertise to deal with. I also didn't know how to braze or weld copper pipes, in addition to charging and dealing with refrigerants, and too many new things at once are scary to me. So here's the more or less finished build. This setup and design is pretty typical of all videos with Peltier plates involved, with a couple of key differences. The idea is that we try and keep high temperatures outside and low temperatures inside. Ultimately, we're really just moving heat around. The plates are sandwiched between a water block and these radiators with thermal paste in between each sides of the plate, and act like tiny heat pumps, pulling heat from one side of their plate, making it cold, and pushing the heat to the other side of the plate. We can use water to move waste heat around into a radiator for temperature exchange. We try and keep the hot side as close to the ambient temperature as possible with heat sinks and fans. None of this is really groundbreaking and has been the basics of air conditioning since it was invented. A big difference for my setup is that the whole system, including the plates, fans, and pump, is about 50 to 55 watts for this very specific setup. I used 8 plates for the cooler, and we'll cover how I got the power draw I did a little later. Another big difference between this build and other builds I've seen on YouTube, and also an important thing to note, is that this is powered directly by a solar panel, which satisfies the primary goal and satisfies the secondary goals with needing no manual intervention to operate, and is able to use the 100 watt solar panel limit I set for myself. There is the caveat that the water pump and fans are using a buck converter to reduce the voltage coming from the panel, but I'll also touch on that later. A neat thing about using Peltier plates is that if you swap the positive and negative flow from the power source, their hot and cold sides will switch, which is useful if you'd like to get heat off of this system instead, and your outside temperatures aren't dramatically colder. This was also useful for me because when I was making the build, I messed up because the temperature exchanges I picked weren't great for their respective sides, and I was able to easily swap the whole hot and cold sides without tearing this apart. I'll go into that later. Much like a heat pump, this build, while already inefficient, will get way less efficient if you are working in temperature extremes, as the plates can only really maintain a temperature difference of like 20 to 50 degrees depending on the voltage supplied. Lastly, when talking about the build, I want to note that insulation is pretty important here, or else you're going to lose a lot of performance, and we don't have a lot of that to begin with. So I've insulated everything that was cold to the best of my abilities, and it had the added benefit of keeping the Peltier plates in place with how I put them together. I used silicone to glue the insulation together and prevent air gaps. I'm sure some of the Peltier plates shifted in the build process and aren't 100% in line with the water blocks, but it was the best I could do with what I had available. A better way to do this would be to have more rigid things in place to keep the plates in line, like brackets or screws, but I also didn't want to introduce conductive heating via the metal screws or brackets from one side to the other, so plastic housing with additional insulation would probably be a better alternative. Here you can see what happens when the solar panels aren't producing their full power. The voltage that's coming across them just kind of goes down. You can see the fan is still running, and the pumps, as you not pictured, are also still running because they don't use as much voltage as the Peltier plates. But really, they just kind of slow down as the voltage gets lower and lower, and then whenever the sun comes back up, as you can see here, it tends to just kind of kick back on in earnest. I'll touch on this a little bit later in the video, but the Peltiers are still technically moving heat, but at a much lower voltage, so they might as well just not be on at all. As for the building process and challenges. To start with, the majority of panels produce voltage that is too high to use for most DC loads. The panels that I chose have a VMP of 19.5 volts, so our first rule is going to be to put ourselves in a position that can use the voltage as is. It's important to note that buck converters are an option here, but there is a way that we can get around having to purchase extra components for this part. It's also not a great way to provide a lot of power because they tend to be more expensive when they're able to handle lots of amps, and they fry pretty quickly whenever you exceed their power limitations. The next couple challenges I faced were related to Peltier plates. One was that their usable ranges are rated from voltages between about 1 volt to their advertised voltages of 12, and they're up to their absolute limit of 14 volts usually. We're being supplied a voltage of 19.5, which will destroy our plates if hooked up directly to them. Also, Peltier plates use way too much power when they're running at their advertised voltages for my purposes, so if possible, we're going to also want to run our plates at a lower voltage to lower our overall power consumption. So luckily, we can use some pretty clever wiring with the plates to get them to the voltages we want from the supplied power source. This also has the added benefit of reducing our overall power consumption from the plates, so we can get them into the wattage ranges we want, and we don't need a buck converter to do it. We're going to look at rewiring resistive loads in series and parallel. For those with more experience in this area than me, take a lot of what I'm about to say with a grain of salt and a large margin of error. The theme of this section is ish. Luckily, there's a lot of wiggle room here for mistakes when working at the power levels I was working with, which is good because it let me find out if I had made any mistakes or if I had any faulty plates without destroying them, which I've done before. At higher power levels, you'd probably want to be more careful how you choose to wire them, but again, for what I was working with, it was fine. So when wiring things in a circuit, you can treat the Peltier plates as resistive loads. For our purposes, they typically have the same resistances as plates of the same type. They vary a bit from plate to plate and change slightly as their temperature changes, assuming none of them are broken, but that doesn't really matter as long as they're in the ballpark of each other. When you put the plates together in series, you can divide the voltages equally across them if the plates are the same types. This was incredibly useful in that I could just use the raw 19.5 volts coming from the panel, and by wiring the similar plates together in series, get that voltage somewhere in the range that the plates wouldn't explode. For example, and what I ended up doing was that I took 4 plates and hooked them up to the power supply of 19.5 volts, and I initially tested this as a bench stock adjustable power supply, which is something I really highly recommend using to make your life a whole lot easier if you want to test things. The plates then used a little under 5 volts-ish, which was well within their operating range and had the added benefit of putting them into their more efficient ranges of operation. A couple of things. I mentioned broken or faulty plates a couple of times before because for my first test with 4 plates in a row, I kept getting very odd voltages across them. 3 of the 4 were running 3.5 to 4 volts, while 1 was using about 6.5. It turns out the one that was using the different voltage was a defect from the factory and I had to swap it out with another one. Once I did that, they all used about the same voltage-ish, plus or minus 10% of each other, and that was good enough for me. This is also a good time to point out that the plus or minus 10% power usage can compound pretty quickly. A half volt difference in power isn't really a big deal at lower voltages because you're still operating in the range of the plates, but at higher voltages, that compounding voltage errors like that could throw you outside the safety range for a plate and break them, so just keep that in mind. As for using a variable step-down buck converter, I used a pretty cheap one during testing that I quickly approached the upper limit on amperage allowed, and it was audibly buzzing and got pretty hot. Like I said before, you need a pretty beefy one to handle more than about 20 to 30 watts. There is also some power loss from using a buck converter, so in order to keep this inefficient project slightly less inefficient, I settled on the series wiring. Also, another important thing to point out, in the same way that faulty plate in the series throughout the whole string, and much like those old Christmas lights, if one plate goes out, the others just won't work, or it could possibly blow because it somehow breaks in a way that puts too much voltage through any one plate. How many watts each plate is going to use with the voltages that you can get by wiring them in series is what we're going to go over next, and was honestly the most frustrating part of this process when it came to initial research. Mostly because Peltier plates have datasheets that are a little confusing to people like me. Specifically, they have graphs that detail amps used at voltages, but it wasn't initially intuitive to me that the amperages lines that they are using are the range of amps, with the label being in the middle. It was also very frustrating because they had gaps in at different voltage levels, which implied that maybe they didn't work at the voltages, which wouldn't make any sense, especially after testing. They used the entire range of amps in a linear fashion, so I know that plates would work in between the 12 volt line and the roughly 10 volt spot on the line. Frustrating, but it could also be because I'm just not familiar enough with the data provided in this way to get what I need out of these graphs. Again, I have a very mild understanding of basic electronics, so you can generally get an idea of how many watts you're going to use by using the power equation for watts and then plugging in the amps and volts. You'll need to do that for each plate and then add the total plates together. I'm not really sure where else to say this, but something that I didn't initially know, but I learned along the way, is that thankfully you don't need to put any sort of amperage limiting device on the Peltier plates. The way you limit their current is by choosing the voltage that you're putting through the plate. Because the graphs typically provided by the manufacturers aren't really great for getting super accurate numbers, I settled on manual testing to make sure I knew what these plates were going to be using whenever I hooked them up at the voltages that I picked. In this next chunk, I'm going to go over testing the plates. Here is my Excel sheet that I used to initially try and math out what plates I would try to use and the voltages. I ended up picking the 12704 plates because they were advertised at 40 watts, and I was able to find them in a 5-pack for not exorbitant prices. The standard plates used in Peltier projects are usually the 12706 plates, but if I explain this well, you should be able to figure out what you need with any plate. Some blessed dude on the internet mentioned that in a forum posting that Peltier plates use voltage and amperage in a linear fashion, and that was a huge breakthrough when I read it because I was too stupid to read the charge. But I did remember doing proportions in middle school math, and it's been one of the more useful math things I've ever mathed. So I figured out that if I knew how many amps I would draw at full power, I could set up a proportion and figure out how many amps I was using at other voltages, and this is what you see me doing here on this chart. To start, I took the power equation and immediately shot myself in the foot by using and inserting the wrong information. I wrongly assumed that full power was 12 volts being run across the plate and it used 40 watts. For what it's worth, full power to use any Peltier plate and how they're typically advertised is 12.5 volts. That half volt makes a huge difference and fixed a lot of confusion when I figured that out later. This is a good spot to mention that the ending numbers that differentiate the plates, such as the 03, 04, 05, and 06, are the maximum amperage that the plate can handle, not what you'd expect to see them using at their advertised voltages. Using the formula of watts equals amps times volts, I was able to get an idea of what amperages the plates would use with the voltages that wiring them in series would get. An example for my 12704 plate, at the voltages I was expecting for having 4 in series with a 19.5 volt supply, I took the 19.5 divided by 4, and that gave me what I thought to be about 4.875 volts per plate. At 40 watts, we know that the plate is using 12.5 volts, so at 40 watts, you're going to have 12.5 volts times amps, and then you're going to solve for the amps, and so you're going to kind of move that around to get 3.2 amps at the end of the day. If at 3.2 amps the plate is using 12.5 volts, what would the plate use at 4.875 volts? We can set up that for the proportion I was talking about before with 3.2 amps divided by 12.5 volts, and then we can just, it will equal X amps over 4.875, and then we solve for X. Here we are solving for X amps, where we'd be getting 1.248 amps. Then we can go back and plug it for the power formula using watts, which is volts times amps. So it's 4.875 volts times 1.248 amps to give us about 6 and some change watts per plate. And then multiply that by 4, and then you can get your total wattage for the whole string, which is about 24 watts. We can then add another string of 4 plates wired in parallel to get about 50 watts of power being used by the plates, with plenty of leftover power to use for the pumps and fans. The order of operations I would suggest if you're trying to replicate this build is to pick your solar panel first so you can know what voltage you're going to get from it, and then use that information to calculate the voltages you would get wiring however many plates in series, and then you can use that to find the amperages of the plate and finally the watts you'd be using. Then you can wire other strings in parallel to get closer to the total watts that you'd like to use. The yellow is my initial testing with a really flawed method, and the green is a second testing that I did, which was much more accurate. For my initial testing, I took a buck converter and hooked it up to the 12-volt wall adapter and just adjusted it manually for each voltage I wanted to see. I read the wattage with a regular wall outlet watt meter. This introduced a lot of inconsistencies in power loss with my results because the compounding inefficiencies of the watt meter and reading the 12-volt AC to DC adapter, which was leading to the DC to DC buck converter of the plate. This was where I figured out that a cheap buck converter, while useful for lower power things, gets blazing hot when you're at or near the amperage limit. As I mentioned before, a basic adjustable bench supplies power source reduced so much confusion when the testing and allowed for much more accurate measurements for the amperage and even did the math for the wattage for me. The green section shows me testing a single plate for power use, the hot and cold side temperatures, with the hot side having a small fan to replicate what it would be like when the build was finished, and I go into the temperature results a little bit later. It was pretty satisfying to see my math guesses for power use here were pretty close to what real-world testing showed for that single plate that I tested. In hindsight, I also got lucky and didn't test a plate that was defective. I'm guessing the margin of error is just slightly different due to the artifacts from manufacturing that pushed the amperages slightly higher or lower, but they were ballpark right and that was good enough for me to move on with the build. This is the part of our build where I actually settled on the 4 in a series for sure because I figured out that the temperature decrease per watt used, with a higher number being better, and found that it was more or less matched the charts I've seen for coefficient of performance for the plates, with the lower voltages giving you more temperature change per watt used up to a certain point. And also, this is where I ran into a build restriction because I wasn't really able to find a good way to fit 5 plates in a line, because most of the heat sinks or water blocks I found have a maximum length of either like 160 millimeters, which is 4 plates in a row, or they were wildly expensive to fit more plates in line without adding a bunch of complicated steps to the process. This would be a good time to talk about the other parts of the build, such as the fan and pumps I would be using. Thankfully, there are plenty of DC fans out there in the form of computer fans, and DC powered pumps are pretty common enough to buy them for not that much money. Unfortunately, they aren't usable in the voltages being provided by the solar panels, but luckily they're low power enough to use those cheap buck converters we've stored along the way without introducing too many inefficiencies. This also allows us to set the fans and pump speeds. I think the buck converter itself used between 0.5 to 2 watts total for the conversion. The fan, pumps, and converting it all together used about like 10 to 15 watts, depending on how you want to set them up. And it kind of depends on how much airflow you need, so it varies. Speaking of airflow, it's also a good time to talk about how important keeping the hot side of the plates as close to ambient temperature as possible is. Specifically dealing with both the heat generated as waste heat by the plates and the heat that is being pulled from the other side of the plate. As mentioned before, the plates really only maintain a temperature difference between one side and the other of about 20 to 50 degrees Celsius, so the lower that you can get the hot side, the better they perform for cooling purposes. I naively thought that the larger-ish heat sinks would be good enough to get the hot sides close enough to ambient, while the radiator would be a good way to pump the cold around. And as you can see here, there's a lot more red than blue, and that larger amount of red is going to the smaller picture and really needs a bigger picture to go into. The blue that is here seems to have more picture than it really needs. That's better. As kind of touched on before, I realized my error in dedicating the, what is now pretty obvious, more capable heat management system with water circulation through a radiator with much more surface area for heat exchange to the cold side, when instead I should have dedicated that robust heat exchange to the hot side that needed it. Essentially, what I was doing was giving a bulldozer to the guy that was digging up some weeds in his garden and gave a wheelbarrow to the guy who needed to clear out some space in a landfill. Cooling capacities and the associated data sheets weren't super helpful because it makes references to cooling specific heat loads a lot, which isn't super helpful because the load I'm trying to cool is essentially infinite, which is the room. So I didn't know how to settle on the voltages I wanted other than using the coefficient of performance charts if available. There are some charts that I found that had helped initially that backed up that one guy talking about the lower voltages leading to better performances, but unfortunately they didn't have a COP chart for my specific plate, so I had to make that on my own. This is the same data I have before, where I used the bench stock power supply, a small fan on the hot side, and just a heatsink on the cold side, where I try to figure out the voltages and amperages used for a single plate, but can be applied to adding more plates, assuming you have the abilities to dissipate the heat generated. The top amps chart just shows us the linear usage of the volts versus amps. The chart on the bottom left is the most useful for us, where it shows that there's definitely a diminishing return for how much power you put into the system versus how much cooling you're going to be able to get back out of there, unless you start changing a lot of things about how you're building this system. I tested two different ways, with the first being the entire build inside, and I would measure the hot and cold sides inside of the house, and then the second way I tested was with the hot parts outside, like the typical AC setup. I would then measure the temperatures on both sides of the plates and then compare them to the ambient temperatures both inside and out. I'm just going to put this in the video because trial and error seems to be a continuing theme, and I wouldn't be doing justice if I didn't include the error parts in the final video. And as I mentioned before, I screwed up with how I managed my heat dissipation and with the initial setup, and these initial tests show how poorly this performs if you don't manage heat well. This was how I did the testing for the build and its performance outside, with the cold being pumped inside, which is what I like to now refer to as the bad setup. The outside testing setup for the bad setup was with the cold being pumped into the house, and then the hot parts were all outside. Here are the results for the bad side testing. So inside you can see that the hot side got to about 99 to 100. Cold side was 5 to 10 below ambient, so roughly 70 to 75. Ambient was like 80 degrees in the room because it's hot in there. The outside testing was what really kind of red flagged this as I was doing something wrong, because the hot side was like 105. The cold side only really got to 100 to 1 to 3 degrees below the inside ambient, which wasn't really useful because inside ambient was 80-ish, so it was only doing 1 or 2 degrees below that, and that really wasn't useful because it means that it can't maintain that temperature differential between the cold and hot side. The reason it took so long for me to figure this out, that I had it set up the wrong way, was I did a lot of this testing inside my air-conditioned house initially and not outside in 95-degree weather, so it gave this kind of false positive better amount of performance when it was configured the wrong way than it should have been. This was my outside testing setup to simulate a 95-degree day with the better setup. By the time I could test with the hot and cold side swapped around, it had cooled off a lot outside, so I couldn't really get similar test conditions if I just threw it outside on my porch. So I took a styrofoam cooler, got the temperature inside to about 95, and then put the radiator into it, and then measured the temperatures that each sides of the plates were giving. I should probably test in a larger area, but this was good enough for my purposes. This was after I switched to the better setup. The better setup gave me markedly improved performances, with the build being better able to keep the hot side closer to ambient temperatures in general. The cold side was lower, with both inside and outside setup enough to, I consider it cooling instead of like not drowning. It's important to note that I do want to test this more apples to apples and have like exact testing conditions to compare it to the bad setup, but I just kind of had to do what I had to do. So you can see that the inside temperatures was hot side of 81, the cold side got about 8 to 10 below ambient, which is similar to the bad setup, but it was more reliably on the 10 side instead of the 5 to 10. The outside was where it really shined and showed the market improvement. The hot side got to about 102, with the cold side being 69, which was like 5 to 7 below ambient. It kind of depended on how long you would let it run. As to the actual cooling power this will provide, it's somewhere between 0 and 50 watts. I have no idea how to calculate a number that it will give me in a way that it can compare it apples to the goat of the standard AC unit. For what it's worth, I do know that due to the nature of Peltier plates, a good bit of that 50 watts, depending on the voltage being used, is wasted heat power, and the plates themselves just heat up because they have electricity running through them, which is where a lot of their inefficiencies come from. So now we can talk about ways to improve the build, and for this section I'm going to go to start with the least impactful improvements I could make, or at least I could think I could make, to probably the most impactful. So from the some of the lesser ways that I can improve, but that would probably make a market improvement, is better insulation for the hot stuff. Given that I had the hot stuff outside already, I feel like I did an okay job on keeping the really exposed hot parts insulated, but I know that I'm losing some performance with the cheaper insulation I use, the tubes carrying the hot water outside not being perfectly fitted, possible air gaps, the heat sink on the buck converters being inside, things like that. In the same vein, I feel like I did an okay job of keeping the plates on their respective heat sinks, but with how I secured them in place, I can't actually see without tearing the thing apart, so I'm guessing that they might have shifted a little bit. I think there might be also some room for improvement with the thermal paste I used, considering I just went with the most amount of paste I could get for the least amount of money, since I knew I was going to probably screw up a couple times and waste a bunch of paste, which is exactly what I did. A larger improvement for the setup overall would probably been improved airflow for both cold and hot sides. I don't think me just sitting a fan on the radiator for the cold side is the best way to move air around the heatsink, but the alternatives were kind of getting into specialty size fans or channeling air, and so for now it's just good enough. I think I did okay for this prototype, but I was really trying to conserve my power budgets for mainly the plates, so I skimmed down on dedicating a whole lot to the fans and pumps. Also, my buck converters started to get a bit warmer when the fans I had were at full blast after tinkering with them. I would need to spend a lot of time trying to figure out the sweet spot for the fans, to radiators, to heat sink speeds and sizes, but at initial glance, there was a lot of complicated math to trying to figure that out, so trial and error is the best way to go about that, and I can probably do that later, but I didn't really bother for now. The other thing I think would really help and probably make the biggest difference would be increasing the water reservoir of water on the hot side and holding it into a container that can get to ambient temperatures passively. The build now relies on trying to actively cool off the smaller amount of water in the build, which is less than a half gallon's worth of water. With water's ability to absorb a lot of heat, it makes sense that the more that you have of it, the more heat you could dump into the system without needing to actively cool it, or the less impact the Peltiers would have on the water's temperature overall, since there's so much of it. I think that if you had a lot of water sitting in a shady spot outside, you could get away with not having to actively cool it, instead just maybe using a pump to run it through some radiator for shits and giggles. But really, the sheer amount of liquid would be enough to compensate. For best performance, I'd say an active fan on some radiators with a large reservoir. Evaporative cooling for the water is an option, but I don't really like that as much because it adds a small amount of maintenance and I'm incredibly lazy. It also introduces an open container that mosquitoes can use for another breeding ground in addition to the thousands of other ones that they find outside, and I'd like to keep it closed loop if possible, but for sheer efficiency's sake, I think that evaporative cooling would be a great idea, and even more so if you were in a drier climate. Lastly, you could consider not using Peltier plates in the wait a minute. So some odds and ends to keep in mind. Some of this is common knowledge or might be repeat of stuff from before in the video, but I just want to make sure I included it somewhere. The reason I specified that I was using a 100 watt panel instead of 100 watts is that a solar panel wattage is never really the full watts unless it's in perfect conditions. So I purposely undershot the wattage I wanted to end up with just to ensure that the build would work with more often than not with a 100 watt panel. You can try to push to higher wattages, but when the panel can't produce the current that it needs for the voltages it's wired for, it does some odd things. It doesn't really hurt anything, but it barely moves the heat around. This was another point that I didn't know going into the project, and I'm probably not the best to try to explain it, but here we go. For me, it was best to think of the solar panels as producers of current more than producers of volts. There is a pool of current that you're pulling from via a pipe, which is the voltage from the panels, so we can kind of keep with the classic water analogy. Once you get to the current limit that your panel can produce, your voltage pipe that you are using to pull that current will shrink until it meets the demands of the voltage, or until it closes completely so it can stay in compliance with Ohm's law. A guy on the internet for some of the question and answer forums I've seen mentioned that if it can't meet the demand that your voltage is requiring, then your voltage just kind of collapses until it does. Again, to stay in line with Ohm's law. For the Peltier plates, that typically means that when the panel it's connected to is producing less power than the plates it needs, the plates across the voltages that show across them are well below what you'd expect when wiring them, so they can match up with the available current, and then that the total voltage the panel is producing is much lower than in this case, 19.5. Or at least that's my understanding of it. But when this happens, the plates end up using so little power, like less than a watt, that they might as well be off. This doesn't damage the panel or the plates or, in this case, the fans, as long as they are meant to be able to be used from the full range voltages. And I'm pretty sure resistive heaters have the same issue with panels. And the guy I mentioned working with the Peltier plates at larger scale did a video relating to this. There's probably a better video on this somewhere, but this helped me understand what was happening and that I wasn't going to blow anything up. Oh my god, I've been recording forever! Is this efficient? As I said before in the beginning of the video, no, these are not. I cannot stress enough that this is a specialty niche thing that I'm doing for shits and giggles, and to specifically explore the directly connected to solar panels idea. You might also be wondering, is this cost efficient? Now, with the thing you have to keep in mind is that things that bring you happiness are priceless. So no, this project was not cost efficient. Generally speaking, if I would have done this perfectly right the first time, I would have spent the following on the parts I needed. Unfortunately for me, I did not do it right the first time, and I ended up with a lot of extra, like, everything. There are a lot of places that you can cut corner or save money, but I wanted to make sure that I was upfront with what this was going to cost someone if they just wanted to do this from scratch. And you're looking at a ballpark of about like $260 if you're doing this from start to finish. This also assumes that you have some basic tools and stuff like wire strippers around, maybe soldering iron connectors laying around that can handle the currents that you're working with. It's worth noting that I gave exact prices for some of the things I purchased, but then I also just kind of gave a best guess for things I didn't purchase but had laying around. Generally speaking, I know that a lot of people just don't have a bunch of this stuff just laying around, so I included them with the breakdown just in case. So if I'm being generous, a 50-watt cooler is $260, which can get you like 2 window units for that price. So no, this is not cost efficient. Now that we've gotten the cons out of the way, I would like to address some of the good things about this, and we can talk about the pros of the build. So this build was made to address a very specific limitation and or problem of directly connecting to the solar panels. I've accomplished that goal. There are plenty of things that say they are solar powered, but they typically are done through an intermediary of a charge controller leading to a battery, leading to an inverter. This kind of setup is very flexible in what it can do, but it does come with its own, admittedly far fewer, limitations and challenges. With the hands-off maintenance approach in mind, it just kind of works. When the sun is out, it's on. When the sun is down, it's off. With the knowledge that this is not really replacing anything, it's great for supplementing existing structures. Theoretically, the plates have a really long lifetime, even longer than advertised when you run them at lower voltages. So I'll probably have to replace the fans and pumps before anything else. While the initial cost in the setup wasn't great, the long-term cost is incredibly low. The individual parts are cheap, and importantly, you aren't paying for electricity. You don't need any specialty training to work with this like you would have to do for refrigerant-based systems because it's pretty simple DC circuits, assuming you take basic electrical safety into account. As I've stated before, this was really only intended to use for small-scale things, and it does that pretty well, all things considered. It's one of the few things I've seen that works for less than 100 watts that actually cools, other than, a generic fan, and then there's also the swamp coolers, but those have some pretty serious limitations. Or, in the fan's case, they're just kind of moving air around so you don't feel as hot. They're not actually, cooling. But an added benefit of how this build was made is that it's scalable. This is getting a little more detailed than you'd probably like, and there are some huge asterisks associated with the following ideas, but seeing as how I wired it with 40-watt Peltiers, and there are 8 in total, I'm only really using 50 watts. If I wanted to use them all at their rated power, I'd be using 320 watts for the plates. So my build is about 15% as much power as I could be pushing through the plates. If that isn't enough power for you, you could always use more powerful plates like the 12706 plates that are advertised for the 60 watts apiece to get to 480 watts. Also, if you wanted to fight God, you could potentially go for the 12715s, which are advertised at 180 watts, so you'd be looking at 864 watts. As for those asterisks you were wondering about, this also really doesn't take into the account how you get them into the appropriate voltage ranges if you're still wiring them directly to solar panels. But a lot of panels I've seen on Amazon are going from like 18 to 24 volts, which is easily cut in two, leading you into the 9 to 12 volt range per plate. And again, the beefy buck converter is always an option since it's clear you're just trying to find the limits of the edge of the universe at this point, and probably not really concerned about power loss. This doesn't take into account the added heat you'd need to dissipate. For me specifically, this lower power setup, I was really only using my fans and pumps at about 6 to 7 volts, so I could have roughly doubled them without replacing them. However, you're definitely going to have to get more powerful fans and pumps if you choose the heresy option to fight God. But then again, you probably have bigger issues on your hands at that point. Honestly, though, at these higher wattages, you're really better off going with a typical AC unit. That doesn't really solve the issue of using the voltage straight from the panels. However, but as I mentioned before, the other guy that did a video and a build talking about using high wattage Peltier AC wired directly to panels, so it's doable. But to get back on track, the point is that the one feature in this build is scalable if I just rewire the existing plates to use higher voltages depending on the power available. And then the only real limits is the panels that I'm working with. If I had a few extra panels laying around, I'd probably up the wattage I put through this thing without too much hassle. And finally, to wrap this up and talk about the real reason I did this, I just think they're neat. Thanks for watching.